Hey class. I wanted to take a moment at the beginning of class before we do our proof of the week uh, to um, to discuss series expansions. The Taylor series for e to the x, sine of x, cosine x, and their hyperbolic equivalents, which you'll see is very closely related to e to the x. Um, okay, so uh, a problem that should be familiar to you from calculus is computing the position of a body, right, in some coordinate system. Um, so if you have a strip of road, then you have some initial position and some final position. Uh, so your position function is equal to your initial position, and if you're not moving, then it's just this constant. It's wherever you were to start. But if you are moving, then it's your initial position, and then you add in however much you've moved since you started. So we'll assume that at time t0, that's when you were at x0, and then every time greater than t0, you are moving at some constant velocity v in the direction towards your fitting end. Right? So between between your initial time and your final time, whenever you cross the finish line, you had this function describe your position. And that's all right. So velocity is going to be measured in miles per hour or meters per second or some distance per unit time. So that when you multiply by time, so distance divided by time times time, gives you distance, right? So meters per second times seconds gives you some measure of meters, miles per hour times hours gives you some measure of hours. Okay, that's great, but what if we're in a race and we're pressing our foot on the gas? Then aren't we accelerating? Shouldn't we account for some non-constant velocity? Okay, yeah, we can we can account for that. So then, really, you're going to change your perspective of this as some velocity for a given time. So your velocity at that instant in time, or times that time. But really, that's if velocity is varying, that's not really what you need. You need to account for all of the velocity that's there. So really, it's more of an integral. With respect to changes in time, so that you're accounting for all of the time along the way. So let's start over and look at it again. Let's consider velocity as what we're trying to figure out. So what is our velocity at a given instant? Okay, so if we have constant acceleration, then our velocity is going to be um, the uh, um, the acceleration times the amount of time that's elapsed since we started measuring, right? If we're increasing at our velocity at a rate of 9.8 meters per second, then every second we should expect to have a velocity that's 9.8 meters per second faster. So if after 1 second we're falling at a rate of 9.8 meters per second, then after 2 seconds we would expect to be falling at a rate of 19.6 meters per second. After 3 seconds, it should be 29.4 meters per second, and so forth. So assuming there's no wind resistance, we'll continue to fall faster and faster. So we'll continue our acceleration. Okay. What if acceleration is varying? So it doesn't make sense necessarily to have a constant, right? If we have a car, and we're going from parked to drag racing speeds, then not only is our velocity changing, but our acceleration is going from 0 to some value. So how do we do that? Okay. So the third derivative, and doesn't come up often, of position with respect to time is called jerk. And so it's the change in acceleration. So you experience a jerk, or it's named that because it's a jolting, right? Like if you're changing acceleration, you're going back and forth or whatever. It's really hard to continue to heap acceleration upon acceleration. And so you're really measuring like variance with respect to time. But assume that it's constant, it's moving forward, then you could use this formula. So you start off at this initial acceleration, and then you tack this on over time. Okay, well, how do we now feed this back in, right? And do we need to measure jerk, right? And so you end up playing this infinite game. So just like with the irrational numbers, how it's a series of an infinite number of corrections to try to pin down this irrational relationship. Right? Like for pi, this irrational relationship between the diameter of a circle and its circumference. So they're both finite. We can take a look at them and be like, yeah, that's the same thing. But the ratio, it's impossible to pin down. It takes an infinite series of corrections to converge to a value, and then eventually you just have to cut it off. But okay, so we play this infinite series of corrections, not just with these irrational numbers, but with functions which vary with time, or which vary with respect to some input. So in terms of position, you would have, like, let's say that we're really just dealing with these. So we have it could be that we're not actually varying our acceleration at all, but we have some function, and we'll cut it off here, which varies our acceleration with respect to time. So we want to know how much of that we're claiming with respect to some time. Right, so we could use the triple prime notation or whatever, but really it's the third derivative with respect to position or of position with respect to time. And then it's, oh, yes, my mistake. So it's the third derivative, so it's some initial acceleration plus whatever we gained between whenever we started and whenever we stopped. And we're integrating this once because we only want to know how much we gained in that time with respect to how much acceleration we gained based on our the jerk that was applied over that amount of time. So then we have this, and now we have a function for a of t. So we can use that and figure out what our velocity is at some point in time t. Okay, so we have that second derivative, so how much it's accelerating, and then that's essentially our initial value at that point. But that gives us the third derivative, the integral that we inherited from over here. And then we do the same thing again, and so we integrate to take into account all of these previous values. So that our final formula, okay. For position with respect to time is ends up taking into account the initial position plus the amount of velocity that we've moved plus the amount of acceleration that we've applied over that next step plus the amount of jerk that we've applied over that next step. And so we could consider this infinite series where we continue to correct that previous function, and we continue to try and correct it with a further approximation. And it's driven, these contributions, these corrections, are driven down by n factorial, and they require increasingly higher order derivatives. And if it's ever zero, then it's zero forever after, so you can cut the series off. And so the nth order derivative and then the time step component raised to the n. So this is shrinking to 0, so the fact that it's raised to the n actually shrinks it even further. So this works in conjunction with this to drive those contributions of the higher order derivatives down to 0 pretty quickly. So that really, you don't need to spend a whole lot of time accounting for them. But that concept that you're correcting your position, or whatever value it is that you're measuring, with some correction with the first order derivative. So in terms of position, we're correcting it with velocity over some amount of time. And then we correct the velocity with some acceleration contribution. We correct the acceleration with some jerk contribution. We correct the jerk with some snap contribution, and so on, all those higher order derivatives. And so that concept, like, you can look at it and you can consider all of these other series, so that you can end up with this general form. And that gives you this general form where you have some known value, you have a value that you know at some point in time, and we'll call that value f of a. And then you want to know where it's going to be at some value f of a plus h. And so you have some knowledge of what's going on here. You know that it has a derivative of change, a first derivative at this point, at that known point. You know that it has this going on. And so you can predict based on, like, if you take a small enough step size, then you can predict where it's going to be using this correction. So you know that it's the function is moving in a certain direction at that point in time, and so you adjust it for the rate times that step. We'll call it h here, and then you account for that second derivative, and it's scaled down by 1 over 2 factorial, because that's the number of times you've had to integrate it in order to get the position. Right? So we're not even looking for derivatives. We're using the derivatives to account for where this function should be, given some initial position, and then all of these corrections. And so each of the higher order derivatives contributes increasingly less and less, makes an increasingly smaller and smaller contributions to the tune of 1 over n factorial, so that the nth derivative is contributing 1 over n factorial. And then we're also taking these smaller and smaller these measurements that are closer and closer together. And so those two combined, again, make sure that all of these higher order terms are contributing much, much less than originally thought, or than these early terms. Right? So this pattern of initial value plus first order correction plus second order correction all the way up to, you could go infinitely far with these if it's infinitely differentiable, and make all those corrections. And if you go all the way to infinity, then your measurement is exact. Or if you reach a point where the derivative of whatever order and beyond is zero, then again, you can measure these exactly, so that if you know those values at one point in time, and you have some initial value at some point f of a, then you can get every value in the function moving forward on that knowledge set. And so even if h gets larger and larger, you can actually measure the function just using that initial knowledge, and then that infinite series of corrections, or potentially a finite series of corrections. So you can know it exactly without having to have the actual function. And then this, in a sense, if you have that, then these become the coefficients for a polynomial of h, right? So we can just call h time, right? So then we have f of t, and each of these, f of a, and the first derivative of a divided by, 1 factorial, and the second derivative of f of a divided by 2 factorial, and so forth. Those become the coefficients to the polynomial. And so this concept of taking these rates of change and higher order rates of change and some initial knowledge led to this series expansion. So an alternative way to represent functions using polynomials. And so that's how we get, or that's how we can view this definition of the exponential function. So okay, so what other functions can we do this for? It's not clear initially, but in theory, anything that has a derivative, anything that's continuous, we can use this if we know that derivative and that order of derivative. And so that's what the Taylor series gives us. But let's do a trick, and we're gonna plug in actually a complex number here, and we'll see what happens there. So what happens if we actually, instead of e to the x, we plug in e to the ix, right? So I is defined to be the square root of -1. So okay, so the only thing we've done so far is we've replaced this value here, so x with ix. So over here we replaced x with ix. Good algebraic skills. Okay, so now we're going to see that the series is split. So there's going to be a complex value for all of the odd values of n, and a real value for all of the even values of n. Because I squared is -1, I to the 4th is 1, I to the 6th is -1, I to the 8th is 1. And so that the lateral component, the complex component, the imaginary component, whatever you want to call it, it disappears on those even terms for this series, because n is in the exponent. And then it's present for all of the odd ones. So let's split it up into a series of even and odd terms, and then see what we get. Okay, so we didn't actually end up changing our indices, but what we did is change the way that we counted, so that when n equals 1 here, we start with 1, and then we go to the third term of our original series, and then the fifth term, and then the seventh term, and so forth. And then over here, we're counting by twos, so we start with the 0th term, and then the second term, and then the fourth term, and so on. And so we can manipulate the exponents to, over here, extract the I, and then in both places, change it so that we're alternating sign on every term. Okay, so now we have this I that's sitting over here for every term. And then the alternation term now changes with every term in our new series. And the x and the denominator are still moving forward at the rate of 2n plus 1, right? So we have to keep the odd terms from the original series. And then over here, again, we have the alternation of sign for every n. But then we're still dealing with those even terms in the x to the 2n and 2n factorial in the denominator. So this gives us two series. And they're both limits. And so for the one with the odd terms, the one that has I as a factor in every one, we can just pull it out to the front because every term has it. And then for the even terms, we don't have to deal with that. And so what we get is something for the odd ones. X minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial and so forth, right? So we have all of the odd terms from that original series with the sign alternating. And this is, in fact, the series expansion for sine of x. And the even one is the series expansion for cosine of x. So that this is, in fact, uh, the odd series is I times sine of x, and the even series is cosine of x. So that we're adding this, whatever's in this exponent, to we're breaking it down. So it's not necessarily behaving like the exponential function that we're so familiar with, where you continue to increase this value, it shoots off to infinity. It's actually moving around in a circle in the complex plane, so that this argument, and that's what we call it, so I times whatever this is actually an angle in the complex plane. So the real part is given by cosine of x, and the imaginary component is given by sine of x. And in fact, you see this with because of the exponential function's relation to any number raised to a power. So right, so through that manipulation, any number raised to a purely imaginary exponent is going to be of the form e to the I times whatever that argument was in the original number, x times the natural log of whatever the base was. So that if you're just going straight up the plane, then the function that maps it is just going around in a circle whenever you evaluate it in terms of complex numbers. And so this relationship was discovered. Is going to be it's either Euler or Cauchy. I'm pretty sure it's Euler, which again contributes to my affinity for him. So this relationship shows this this really interesting connection between the exponential function and the complex numbers. And so it was discovered at a time when complex numbers weren't fully understood or even accepted as real, which is why they're called imaginary numbers. And so Euler was pushing to call them lateral components to the real numbers. But they are derived from this solution to the square root of -1, the need for a solution to that problem, so that you have closure over those geometric numbers, through the negative range of the real numbers as well. So this was discovered and hinted at the need for complex numbers even before the real numbers were accepted as distinct from the rational numbers. So it's interesting that it moved, that mathematics was moving forward at that pace. Anyway, okay, so those are the series expansions for e to the x, sine of x, and cosine of x. And so I'm going to mention it just because I never knew what the hyperbolic functions were. And so there is a relationship between e to the x and hyperbolic sine of x and hyperbolic cosine of x. So those are noted. Sine h of x and cosine h of x. And it's the same terms in the same order, except that you're no longer alternating sign. Everything is strictly positive. So that so if you just add these two series together, you get e to the x. You get that original series. So they're significantly less interesting than the trig functions. Okay, so this is the that idea that if you have this infinite series of differentials, that you can patch them together to make a polynomial that that gives you, these. You can call it an approximation, and that's if you cut the series off. Otherwise, if you go to the limit, then it is the actual value. It defines these functions. So we can compute them. Given a loop in a computer, we can come up with our own functions for each of these, our own definitions for each of these 5 functions, e to the x and hyperbolic sine and cosine and regular sine and cosine. Okay, so let's jump into our proof. And we're going to extend gamma from last week. Okay, so gamma was this continuation of, and eventually the analytic continuation of the factorial function, where we defined it as so we define it as gamma of n is equal to n minus 1 times gamma of n minus 1. And when n is an integer, then that's equivalent to n minus 1 factorial, or whenever it's a positive integer. Okay, so that's great. So what about values in between? So one special value that's about to come up, and we'll have to treat it, is so gamma of 1/2 is equal to the square root of pi. And zero chance that we have time to go over the proof. I didn't prepare for it anyway, so I would draw it out anyway. But just we'll state that gamma of 1/2 is equal to pi, so that we have this. So this is that functional definition, right? So where we define it recursively, essentially, using this n minus 1 times gamma of n minus 1. So that applies even when it's not an integer. The factorial only applies whenever it is an integer, or positive integer. So that if we plug in something like this, then we end up with this, right, which is, right, because it's 1 plus 1/2 minus 1, well, those two cancel out, and you just end up with a half times gamma of a half. So we end up with 1/2 square root of pi. If we were to do gamma of 2 plus 1/2, then we would get that recursive definition, so that it's 1.5 times this result, and so forth, right? So it's defined at the half values as well as at the integers. And so there's a duplication formula that we're going to take advantage of here. So let's give this definition for gamma, and then I'll point something out, and then we'll jump into the proof, and we'll be done for the day. Okay, so the duplication formula is Okay, so via these, well, not quite constants because this one depends on our input variable, but we have this relationship between gamma of k plus a half, and gamma of 2k, so that this value, which is evaluated twice as far down the line as this one, is given some equivalence, and then we have 2 to 1 minus some power times the square root of pi, and so forth. Okay, so square root of pi we've already discussed. That's going to be relevant because of this plus 1/2 in that recursive definition. So if k is an integer, then it terminates with that square root of pi factor or whatever. So let's do a little bit of manipulation, then the observation. Right? So let's move this over to the other side, and we'll move these over here so we have all the gammas on one side. Okay, so when we have it in this form, we have something where we have this input variable. We have k, or we can call it n if we want. So we have something that's raised to an exponent of our input variable, and then divided by this product of gamma functions. And the numerator is more or less twice the input, or the input for the numerator is more or less twice the input for the denominator function. So k and k plus a half. Right. Okay, so let's just note that if this were k, right? So then we would have something that looked like this: 2k minus 1 factorial divided by k minus 1 factorial times k minus 1 factorial. That's, well, if we insist that, let's do some manipulation, right? So let's redefine 2k as n, right? So n is equal to 2 times k. Then the combinatoric function right, n choose k is n factorial over k factorial times n minus k factorial. But in the case that n is 2k, then this is 2k minus k, when you get k factorial times k factorial on the denominator. Right? And so up here, that would be so this is very nearly the combinatorics function. So we have this hint that we're really close to demonstrating that this function, right, because it's so close to this, essentially grows on the order of the exponential function. Where this would be 2 to the n if we made that 2k substitute, 2 to the n minus 1. Okay. So can we use that to show anything? Well, yeah, I'm going to make an argument that we can. Okay, so But before we jump into that, let's go back uh, to our set mapping function, right? So subsets are these inclusions, right? Okay, so let's start with a set of three elements. So I've the elements are the same as the indices themselves. So index 0, index 1, index 2. So that you could represent this, you could represent all combinations of subsets using 3 bits. Okay? So okay, so we've exhausted the possible subsets just to demonstrate the point. So 2 to the 3 or 8 possible subsets, ranging from the empty set to the sets with just a single choice, to the sets with 2 elements, to the set that includes the entire original set. So this is more than just academic, right? So you can represent the subsets here, these combinations of subsets, using an octal number, or a number that ranges from 0 to 7. Right? And so if we relabel these, read, write, and execute, then you can see the logic behind the chmod utility, which will dictate the file permissions that you have, whether you can read the file, write to the file, or execute the file as a script or a binary file. So you can define permissions using these octal representations. So some number between 0 and 7 will indicate whether or not a given user has the ability to read, write, or execute against a particular file. But that's it's somewhat trivia at the moment. What we're really more concerned with is the idea that there's this correspondence between 2 to the n, where n is the number of sets, right? Okay, so the now previously we've discussed using decision trees, or the idea that you have some function which maps a given input set to some collection of final states. So we're going to ask the question, what is the distinction between the class of problems that can be computed in a polynomial runtime and the class of problems that can verify an answer, given an answer that can be verified in a polynomial runtime. And so are these two exactly the same? So if you can verify something in polynomial runtime, does that mean you can necessarily verify it in, or come up with that solution yourself in polynomial runtime, or is it possible to get something that's on a different plane, so something that's exponential, but that you can verify in either constant or polynomial time? Well, we're going to use the logic that in order to solve the problem, to have an algorithm, you need to be able to map to a final solution space that supports every possible final state for any given input state. And so the trick there is that this logic where you're mapping sets, you're going to need to use that in order to count the number of leaf nodes, the number of possible final states. Okay, so now let's say that we're given some collection of numbers, a set of user IDs for some social network like Facebook or whatever. So that it has n elements. Okay, and then let's, for the sake of argument, say that n is equal to some power of 2. So it doesn't really matter, but we're going to be dividing by 2 here and there, and so it's convenient if we can just assume the output to be an integer. But the results are consistent for values in between. Right? Okay, so we have something that's of the size 2 to the x, and then we want to know for certain size combinations whether or not that particular combination is present. So the combinations themselves, there are you can use a number of size 2 to the n. Right? We don't want to confuse that yet. Right? So there's 2 to the n possible subsets here. Okay, so what if we want to consider a particular class of subsets? So we've narrowed it down, and we want to know, we want to consider now relationships. So the relationships would be modeled using a graph, right? And so 2 vertices are considered adjacent, if the 2 individuals know themselves, and for these purposes, everyone is a friend of themselves, so that we have a reflexive adjacency matrix, and adjacency matrices are, for these simple graphs, they are by nature symmetric as well. So then this, like, we have our adjacency matrix. And then we use it to define all of our relationships. And so we can just tack on, like if we consider this as a string, so this is a string of n zeros and ones, and then this is a string of n zeros and ones, and each row has n entries in it, as n columns in it, so that if we were to just glue each row one right after another, we would end up with a string of length n squared. So So we have something that's on the order of n squared. Okay, so if we want to run a test to see whether or not there's a collection of individuals that all know each other, then we can construct it using the same adjacency matrix. So it's just a different representation, a different adjacency matrix of the same vertices. And so it's and then we just want to test whether or not that subgroup, that proposed subgroup, that clique, is a subset of the given graph, is a subgraph of the given graph. And so one way to do that, whenever you're just dealing with binary numbers, so in the case where we're dealing with the octal set, if we want to know if someone has both read and execute permissions for a file, then that's equivalent to the test. Okay, so you do the bitwise AND operation, and if after doing that, if it's equal to the permission you were testing for, then it has that permission. And then the same thing with the execute permission. And if you want to check for both, then then you perform the bitwise AND, and you see whether or not the output is the same as what you were originally testing for. Okay, so that logic applies for an octal number for 3 bits. If we consider this as a binary number of n squared bits, then that same logic would apply. So we could test whether or not our original network has a given subnetwork by constructing the adjacency matrix for that subnetwork, and then concatenating row after row, so you end up with this string of length n squared, and then you perform this bitwise AND arithmetic on it, and if the master set, the actual graph that you're testing, with the bitwise AND for the subnetwork that you're testing for, is equal to that subnetwork that you were testing for. So once you've gotten rid of all of the peripherals, all of the extraneous stuff, then you have evaluated something that then you have a true-false evaluation for whether or not that subnetwork is there, and you've done it in n squared operations, or something that's going to grow on the order of n squared. So the key is that it's polynomial. Okay, so you can test for the presence of a subnetwork in polynomial time. So then the question is, how do you so we have this potential test for solution. So we can tell whether or not, given a solution, in polynomial time, so that non-deterministic polynomial runtime is there. So is it possible to construct a problem so that, or to ask it in a way so that we can't arrive at that solution in less than exponential time? Okay, well, so now we have this set, and we used it to construct this adjacency matrix. And so what we want to do is manipulate the problem so that we're testing for the presence of subnetworks. Okay, so the number of subnetworks of a given size k, so we have n vertices. So the number of subnetworks of size k is going to be n choose k. So n factorial over k factorial times n minus k factorial. Okay, so we were just looking at this. We were just looking at something that is very close to this. So now we need to consider that that what we're counting isn't the combinations of the original set. It is the final state where we're testing for inclusions of a subset. So now if we serialize, or by serialize I mean if we assign some serial number to each one of these combinations, then we would have n factorial, then we would end up with a set of possible final states on the order of two to the n choose k. Okay, so if that's our number of leaf nodes, then our decision tree, our deterministic algorithm that can correctly arrive at a solution for any input of graph of size n, would be the log, or would be would be the tree height, right? So we would take the log base 2 of the number of leaf nodes that it needs to support, which is n choose k. So our runtime will be on the order of n choose k. So if we can show that that this, right, the exponent for in our tree height, or in our number of leaf nodes, if we can show that this grows on the order of and something that's not in polynomial time, so e to the x or worse, or e to the n in this case, or worse, then we've done it. We've constructed something that we can test for in polynomial time. We can verify that a given solution is either a solution or not, is true or false is solution in polynomial time. So we just need to know what the theoretical best case scenario in this, for the best case algorithm in a worst case scenario for this particular problem is of exponential order. Okay, so what we need to do is get this in the form of two to the n, right? So we need to show that something is happening on exponential order for this. Well, we've already gotten really close. We started off really close. So we'll jump there. We won't demonstrate the algorithm itself, but essentially, whenever all is said and done, the algorithm is that you order every one of these combinations and then you just go. And you can ask, well, can't I optimize the order? The problem is that you can derange the input set so that even if you find some heuristic or whatever, if you find something that hints toward a faster solution in some cases, well, there's going to be inputs that are exactly wrong for your particular approach in trying to speed it up, so that you can't cheat the reaper, essentially. Like the correct solution, the algorithm that will eventually yield whether or not there exists some clique of size k, right, is going to be on this order. Okay, uh, so this value, because of this formulation, is actually going to be maximal whenever n is twice the size, or whenever the set that you're looking for, the subgroup or whatever, is half the size of the total number of vertices in the graph, or in the social case, the number of individuals in your social network or whatever. Okay, so. Okay, so this is the formula we started with, and we now know that if we can just show that that the n choose k formulation is of exponential order, then we're done. We've used the decision tree argument to show that that's really as good as you can do. As far as algorithms go. Okay, and then we'll wrap back around to the Boolean satisfiability representation in a little bit and explain that. Okay, so we started off with that formulation, and we made the same manipulations I showed you before, but over here I had 2 to the n minus 1. Well, minus 1, 2 to the minus 1 is just 1/2, and so here we've moved it down to the denominator. But we have it in that form. This is already n minus 1 factorial. This is n over 2 minus 1 factorial. And then this is still that gamma. Because of this 1/2, we can't factorialize it yet. But we have this, and we have this. I don't think I actually changed anything from this step to this step, so I'm not sure why there's 2 steps there. Okay, so now let's redefine what we're talking about here. So let's call this thing on the left f of n, and so it's a function that grows exponentially with respect to n. And then that's exactly equal to this representation on the right. So we're going to break it up into alpha, beta, and gamma, all with respect to n, functions with respect to n. And so this n minus 1 factorial is going to be our alpha. So alpha, beta, gamma, little gamma, or alpha, beta, and gamma. We're just going to try and manipulate it a little. So using product notation, so it's the same as summation notation, except instead of plus signs, you're multiplying. So instead of addition, you're multiplying. And it ranges from 1 to n minus 1. So that's product notation for the factorial function. And then we're going to do the same thing with beta of n from the denominator, or gamma of n minus 2, which is n over 2 minus 1 factorial. And then this is the product notation for it. Okay, and then gamma is going to be of this form. So we have n over 2 plus 1/2. So that's n minus 1 over 2, n minus 3 over 2, and it's because the difference is 1, right? So it's this minus 1. Well, minus 1 is the same as minus 2 over 2, and so common denominator n minus 3, and so forth, until you get to 1/2 times square root of, or times gamma of 1/2, which is square root of pi. So you get the square root of pi sitting out front, and then you get this product notation. And then now we've defined h of n in terms of what we're trying to show. So we want that n choose k formulation where k is half the value of n. So that would give us n factorial on the top, and then n over 2 factorial times n over 2 factorial. So this is where we're trying to get to, and we want to understand the relationship between the gamma equivalence in relationship to 2 to the n and this. So that's what the work that we're trying to do. Okay, so going back to f of n, we have these 2 equivalent statements from the duplication formula, and we can manipulate it to this, and then we can put it in product notation, and then we can clear out that 2 times square root of pi from over here. So we can get this as just 2 to the n, by multiplying this times the right side of the equation. So we do that here. So now we have f tilde is exactly 2 to the n. And so now we have 2 times this. And the square root of pi canceled out. But we're still left with this inconvenient 1/2 one. And then we have most of what we're looking for over here. So we cancel this out with the first half of this. So this starts at n over 2 now. And now we have just this in the denominator. And so now we go back to h of n, which is our n choose k function. And then we put that in product notation. And we can see just how close we are. And so if we can show that h of n is bounded below by something that's also exponential order, then we have that our combinatorics function grows exponentially, which combined with the tree height argument and decision tree for our algorithm, and by having enumerated the number of final states, the leaf nodes in our program, we can show that we've identified a problem. We'll have shown the distinction between the set of polynomial problems, the set of problems that can be solved in polynomial time, and the set of problems that can be verified non-deterministically in polynomial time. Okay, so we want to show that h of n is bounded below by something that's of exponential order. So we have h of n, which is our combinatorics function. We have f tilde of n, which is 2 to the n, and it's also this. And then we have g of n, which is some function that will transform this, which is greater than h of n, into something that's less than h of n. And so first we're going to look at that exclusively. So we don't know what g of n is just yet, but we know what h of n is. We know what f tilde of n is. And so then we perform some cancellations, and we end up with this relationship, so that this is greater than this, right? Or that's what we're trying to get to. And so we expand both sides of the inequality, right? So we just expand the denominator over here. It's this factorial. We expand this denominator. It's this not quite a factorial. It's a product series. And then g of n, which again we still don't know. So if g of n is constant, then all we're dealing with is the relationship of this to this. So let's set it aside, and let's figure out how the left-hand side, h of n, relates to our f tilde of n. So we set it aside. We use this unknown relationship, or this placeholder relationship notation. And we have this on the left and this on the right if we set aside g of n. So this is n over 2 terms, and this is n over 2 terms, both in the denominator. So we can compare them term by term. And we see that on the left-hand side, 1 over n divided by 2, or 1 over k, whatever you choose, is less than 1 over n over 2 minus 1/2. Right? Because the denominator is 1/2 smaller than what's going on over here. This one is again 1/2 smaller, or the denominator over here is again 1/2 smaller than what's over here. So it swells it just a little bit. And so we can see that it's close, but term by term, the left-hand side is just smaller than what's going on the right-hand side. So we don't have the relationship we want, but it's really close to giving us what we need. So we have this relationship, and it's exactly the opposite of what we're hoping for. So we know that we can't use g of n as a constant, right? So we have to have some function g of n that gets us to where we're trying to go. So we have, so we can't say this just yet. So let's define g of n as this function which cancels out this smallest term and creates a new largest term, so that this is now being compared to this, and this is now being compared to this. So in that relationship, we would have as our smallest comparison, 1 is greater than 1 over 1.5, right? So 1 is greater than 2/3. And then as our largest comparison, we would have 1 divided by n over 2 plus 1/2. Right? So we cancel out our smallest term. We cancel out our smallest term, and then we introduce a new. We cancel out our largest term and introduce a new smallest term. And we add that to the series, or we multiply that by the series that we already had. And then we make our new comparison. And now term by term, we have what we want. F tilde of n times g of n is less than that term on the left-hand side. So that because of the term-by-term analysis, we can now say that the series as a whole on the right is smaller than the series as a whole on the left. And so we have this relationship. And we've identified g of n, which is polynomial. It's the polynomials in the numerator, so it's grows on the order of n minus 1, n to the minus 1, which when multiplied by f of n gets us h of n to be greater. So we have this lower bound, and so we have our exponential over here is now bounded below by, and this was exactly 2 to the n, right? F tilde of n is 2 to the n, and then essentially divide the exponential function by n, and you get a lower bound for our combinatorics function. So so we'll restate that, right? So f tilde of n is 2 to the n, and g of n is this function which kind of rolls our series. It cancels out our largest term, our the denominator, which is doing the least to shrink our f tilde of n function, and replaces it with exactly one term with n to the first power in the denominator, which contributes something that's smaller than the smallest term in our h of n series. And so the product of those two functions, whenever we carry it out, it simplifies to this 2 to the n over n plus 1. So we'll call this phi of n. It represents our lower bound for an optimal algorithm in a worst case scenario. And that is 2 to the n over n plus 1. Okay, well, we have this relationship, and we can see that h of n is greater than phi of n because of that. And so that essentially demonstrates it. So even though we have this division by n over here, and we can't claim that our n squared algorithm for checking a solution is actually optimal. It's just proposed, but you'd have to imagine that any solution would be, or any test of a solution or of a subnetwork would be on the order of n squared, in which case the true relationship for a best case algorithm would be 2 to the n times n, because of that you're multiplying by n squared operations on every pass. So then it truly is exponential, but even this is not in P, and so we can show that using that argument, the collection of problems that can be solved in polynomial time versus the collection of solutions that can be verified in polynomial time are not equivalent sets, because we've constructed a problem where that's the case. Okay, so what does this mean for the satisfiability problem? I believe it was the original reason for this test, right? So, okay. Okay, so it's again that combinations argument. So it's essentially the same thing. So we have our variables, these Boolean values, and so each one of these is going to be true or false, and then we want to know that we want to know whether or not there's some faster way to evaluate this, or whether or not a given problem, of this manner can be tested to see whether or not it's even possible to have some evaluation of true without going through the whole truth table. And using this result, no, really, it's not. If you want to know whether or not some terrible compilation of or composition of these Boolean inputs results in it, then the only way to know for sure, or there's essentially no faster way to know for sure than to test the 0-1 combinations of all of these, right? So in this case, 0 is whether or not this, or false or whatever. So however many inputs you have, if you have n, so on and so forth. You essentially have to try every combination of inputs, using our set inclusions or whatever, and that'll tell you whether or not one of them actually satisfies it. The result is a victory for pessimists everywhere. I think part of the reason that this problem it's proven so difficult through the years is that it's a tough question. The barrier to entry is pretty high, but beyond that, the psychological constraints that in order to attempt the problem, you have to be an optimist, and the result of the problem is the pessimist perspective that you can't achieve some polynomial runtime for every one of those NP problems. And so those conflicting perspectives on life, that you needed an optimist to try a pessimist point of view, is on top of barrier to entry and difficulty of the problem or whatever. I think that lended to the longevity of the problem. Okay, anyway, we're over on time. Next time we will do almost certainly another lecture. Okay, so we'll introduce another special function, and then we'll do another example of an API and a combined with a single page application, web front end. Okay, have a great evening. Talk to you next time.